record on this computer for now. All right, we are recording. I'll work out the details with Hayden afterward on how to get this all shared with everyone. So anyway, I'm TJ, I'm a postdoc, and I am not particularly interested in just talking at you. And it's nice because this is a small group, so there's not a lot of effort that really needs to go towards keeping us on track and getting us to the end. So feel free to speak up and ask questions. This is not meant to be a formal sort of interactive walkthrough of how to do something in particular. What I'm really interested in doing today is to show you at sort of a higher level what else can be done with CompuCell besides what we've primarily been doing throughout the week. Hey Lorenzo, welcome. And sort of point you in the right direction as far as what infrastructure is available and what using CompuCell in more of basic Python applications can look like. And so, yeah, use the chat or just unmute and ask questions. Javid. Also, if I'm butchering your name, please just speak up and correct me, and apologies in advance. Javid?
Yeah, it is Javid.
Great. Yeah, so I'm certainly the person to help you with the compilation stuff, but how about let's connect after the workshop?
Okay.
Yeah, usually the compilation issues is just, fairly simple.
Yeah, I know.
So,
okay.
But yeah, let's connect outside of live time and work it out together.
Okay.
Great.
Thank you.
Yeah, no problem. But again, so unmute or ask questions in the chat, whatever you're comfortable with. Just speak up if anything's unclear or if you want to know more about something. If it's coming up, I'll just let you know. But really where I'd like to start today is to sort of point out maybe what might already be obvious to everyone here, but that as we've progressed through the week from pretty much de novo, no CompuCell whatsoever, all the way to where we currently are, we've sort of been working in this kind of predefined space that Twedit creates for us, and then, like generating Python code and XML based on the template that Twedit provides, and then migrating that over to Player and doing interactive execution. And maybe it's sort of invoked a question in some of you that, well, what else can you do with CompuCell? We're doing Python stuff in our Steppables and in our script where we define our Steppables. And so is it possible to go beyond that and to use CompuCell in maybe ways besides what Twedit really sets you up for? And so that's what we're going to do. We're going to look at what it takes to execute a CompuCell simulation in more of just a basic Python script, or even an interactive terminal, and sort of putting CompuCell in more of a broader context of, say, something like an outside world, programmatically, that you have things going on inside your Steppables as they're being called, and CompuCell is doing all of these things. But what if CompuCell is integrated in your particular application? How would you use CompuCell in ways besides what Twedit and Player really set you up for? And so we really want to move in this time together. What I want to do is sort of take all of us into a space where we can think about moving beyond just what we've been doing of implementing CompuCell models and simulations in Twedit, and venturing more into the realm of using the CompuCell Python API to be able to, say, work in existing Python software and do CompuCell simulation tasks and data analysis, but within something like an integrated scenario. So is that clear so far? Any questions I can answer before we sort of start diving into the weeds a little bit? Again, just shout at me or put something in the chat. Shout at me if you put something in the chat and I didn't notice. Otherwise, so this is sort of how I'd like for us to think about this, because this is really a lot of the motivation in the first place. This is one of the very first things that I worked on when I started working with James, just essentially doing something like black boxing CompuCell. We all week have been working, especially with the Steppable interface. Every time we go to do anything in Python for CompuCell, we start with this predefined Steppable that Twedit generates for us, and we write things that go on inside of our functions that then CompuCell will go on later to call when we execute our simulations. And the question here that I asked that this work addresses, this capability now provides, is, well, what if you want to treat the entire CompuCell simulation like a function? Where you say pass information into a function that will then go on to do CompuCell things internally and then return results. So something like creating just a simple function and doing CompuCell stuff inside that function, which, maybe it's obvious to everyone, but I'm going to say it because I think it's awesome. That, this essentially sets CompuCell up to function as the computational core for a lot of advanced and integrated applications. We see this a lot in a lot of engineering disciplines, especially in industry, where you have these very expensive simulations to simulate things like car crashes, for design for crash worthiness, or predicting flight performance and the mechanical health of an airplane, even as it's running. These sorts of applications can then take CompuCell and use that as the computational backend for applications like model calibration, digital twins, massively parallel, computing environments of, launching upwards of hundreds to even thousands of simulations just by repeatedly calling a function that will then go on to execute a CompuCell simulation. And so that's sort of the motivation here. And we're going to go into some specific details about what's necessary to be able to do that, what infrastructure is in place currently to support doing that and doing it efficiently. And if we have time, I also snuck some slides in on some teasers for current work that we're doing to sort of take this to the next level and honestly kind of blur the boundary between what is the outside world, outside of a CompuCell simulation, and what's going on inside of it. Now, one of the nice things about doing this, just to start, is that setting up a CompuCell simulation to be executed in something like an integrated application or just in basic Python script doesn't necessarily require any actual modification to the project structure that Twedit generates. So quite literally, everything that you've developed so far in all of your learning experiences throughout the week, you can take every single one of them and just write a Python script that uses it, but in an integrated way. And so oftentimes, in real research workflows, this is what this looks like. For the few people who I've really gotten to actually start using this capability so far, this is very new, is that, Twedit and Player provide a means for developing the simulation, testing the simulation, using all of the really nice features that Twedit provides for productivity concerning like, generating the actual implementations of things like loops over cells and attaching SBML models or antimony models to cells and all of that. That's all great, but very often in real research applications that you sort of move to the next level in the progression of a project where you want to start doing things like using that simulation in high performance computing environments. And so this work is set up in such a way that you can quite literally take what you've developed in your prototyping and your simulation specific work and at the very least, just write a basic Python script that can use that to execute it on your cluster or plug it into your optimization algorithms. And so to start on like actually being able to do this, there are a couple of important details technically that I wanted to really drive home here, because my hope is that all of you will sort of run off and start using CompuCell as a Python module in lots of interesting software applications. And so what I really want to drive home here is how to hit the ground running on how to do this. And so we're already going to jump into some sort of interactive type learning here. So let me just ask now, who here has worked with or is at least familiar with Conda? And I'm sorry if this seems like a total digression, but we're going to talk about other software now. So Conda, Anaconda, Mini Conda. All right, now Shane has worked with Conda or is at least familiar with what it is. So Conda is an excellent package manager. And I'm not going to go on my advocacy for the whole world using Conda, but I am clearly a fan and I use it with every project that I develop, both for setting up build environments as well as for providing distributables. So CompuCell is distributed through Conda. And even with the local installer that we've directed everyone to as an alternative to the NanoHub tool, even that local installer actually does most of its work using Conda. And so we distribute CompuCell primarily in two different ways, one being with the local installer that you may have used. But maybe you noticed when some of the terminals started popping up that really a lot of that work was actually just redirecting work to Conda, which was actually just fetching the Conda CompuCell package. So CompuCell is distributed on the CompuCell3D channel. And so aside from using the local installer to go and do the work for you, you can actually install the entire CompuCell package with both of the GUIs, as well as the entire computational core with the pre-built binaries. You can install that into any currently Python 3.7 Conda environment. We're expanding the Python support up through at least 3.9 as a current activity. But for now, you can also actually just ditch the local installer altogether and instead just install CompuCell3D into an existing Conda environment. And so a lot of the motivation for doing that, aside from having Conda's infrastructure do the work for us with providing dependencies, is that it also greatly simplifies setting up the environment for you to be able to interactively execute CompuCell in a Python environment. And so for those of you who aren't familiar with Conda or haven't really worked with it in the past, this essentially boils down to a two-step process for being able to actually execute CompuCell in a Python environment. And the first step is to do what's called activating the environment. So if you either use the local installer or you install CompuCell into an existing Conda environment, the necessary step to do for setup is to do what's called activation of the environment. And we'll look at what that looks like in a couple of different scenarios. And then after that, you do whatever you want. With the real sort of starting point is that in a Python script or just in a terminal, you can have Python going and be able to successfully execute the Python command import CC3D. And Conda greatly simplifies that. And so activating the Conda environment and then doing whatever you want. Now, to handle the prospect of people not having Conda installed already, CC3D is distributed with a version of mini Conda that actually is what's used during the local installation. And this kind of creates a couple of different possible scenarios for how to actually get the environment going. Probably all of this you could figure out on, Stack Overflow or whatnot, but just, for your internal notes and then just to make you aware of it to start, just to mitigate some potential frustration. We got a couple of different scenarios here where either you say don't have either Anaconda or Mini Conda installed, in which case you can just use the Mini Conda distribution inside of CompuCell and just use that to activate the environment that CompuCell is built on. And so actually I have a terminal going. Pedro, is Anaconda fine? Yes, Anaconda is perfectly fine. I use Mini Conda, but I've got a few friends who do all of this work in an actual Anaconda prompt, and all works the same. For those of you who don't have Mini Conda or Anaconda already installed, you can, in a terminal, just navigate to the root directory of your CompuCell installation, and you'll find, here I have a terminal up here, so I have a version of CompuCell installed here in CompuCell3D, and I've got Mini Conda right here. So that's the Conda environment that CompuCell is linked to, essentially. And yeah, so you can do something as simple as just saying, all Mini Conda 3, Conda bin, activate. And so for those of you who have maybe worked with Conda in the past, you might notice that this actually didn't activate the Mini Conda 3 environment for me. And that's because I'm operating in a sort of different environment, which is that I already have Mini Conda installed, in which case this actually activated the base environment of my Mini Conda installation. And so for those of you who are in this particular sort of scenario, you can also instead just use your actual Conda installation to activate the environment just by activating according to the path. So you can do something like call Conda activate and just pass the actual path to the installation. And I get all this junk, and there you go. So for those of you who have Conda installed and have used the local installer, you can just use your root or your system installation of Anaconda or Mini Conda. And when you call activate, just pass the path to the Mini Conda 3 directory in the CompuCell installation. And it's a valid Conda environment that Conda itself installed. So you can use it pretty much out of the box. And the easiest scenario with the most setup required beforehand, though, is that if you do already have Conda installed, then you can just install CompuCell through the CompuCell3D channel. So, Nasheen, what else will we use in Anaconda? For our particular applications today, nothing necessarily. That being said, and one of the main motivations for moving to this distribution strategy is everything else that's readily available through Conda, whether through Conda Forge or, really, sort of massive channels like Bioconda. There is a ton of software that you can install by just doing something as simple as typing Conda install and whether it's CompuCell3D or something else. I think the last count I saw was over 7,000 software packages, many of which are in scientific computing. And all of those can be integrated into the same environment. So we're talking about the possibility of being able to have CompuCell3D and PyTorch, or some other, machine learning or artificial intelligence or advanced, optimization, image segmentation is all just right there. And all sort of waiting to be put together into the same Python software to develop these very advanced biological simulations and numerical and computational workflows. So the sky's sort of the limit, and that's a really good question. Okay, so if everyone's with me, at least conceptually, then we can move on to actually like getting into some of the guts of this. But what you should find is that when you go through this process, however you did it, that you can just type Python and then import CC3D. It's going to load the binaries, and that's it. I can create a steppable right now, can initialize CompuCell, all of the stuff that Twedit set up in that template can do, but just in a basic, just live terminal, just like this. All right.
I didn't understand exactly how to activate CC3D in Honda.
I'm sorry, could you ask again, Pedro? I didn't quite hear you.
I didn't understand exactly how to activate. In my case, I don't have mini conda and there's no conda package inside my CompuCell. So this command wouldn't work for me.
Yeah, so did you use the local installer?
Yes.
Yeah, so what you should find is that when you navigate to the CompuCell3D directory where the installation was placed, you should find that there's a directory called miniconda3.
No.
There's no, is there some, what may be named ENV?
I am using version 4.2.5.
Oh, yeah. Okay. So sorry, Pedro, thanks for bringing this up. This is a great question.
Okay.
So all of this is as of version 4.3.0. Okay, so mine are
4.1 works as well.
So 4.2.5 was the last version to go out without this. So we released version 4.3 maybe a month or two ago. And we're now on 4.3.1. So if you go and download the latest package or the version before that, this is how CompuCell looks now. If you're using an older version, then yeah, you won't find this. And sorry, Pedro, and sorry, everyone, I forgot to bring that up. As I said, this is some really new work. And so okay, question in the chat. How do I import CC3D in the Anaconda prompt? Yeah, okay. So what this, actually, let me reset my terminal and we can just do this together. Okay, so if you have CompuCell installed, then you can open a terminal and navigate to the root directory of the installation. If you're in NanoHub, you cannot do this. Technically, there is a way, but it's really hacky and it would just be less harm or more harm than help. Okay, so yeah, you can do this in an Anaconda prompt or just a basic terminal. Make the root directory of the installation your current directory. And if you're in an Anaconda prompt, then you can just do something like conda activate miniconda3. So if you have CompuCell installed with version 4.3 or greater, then this will work. If you're working from an Anaconda prompt or you have miniconda on your system path, this will also work. If you don't have Anaconda or mini conda. Well, you actually technically still do because CompuCell installed it for you. And in that case, if you're working from the root directory of the installation, then you can do on Windows call and then miniconda 3 / conda bin / activate. On Mac and Linux, you can just convert this, change call to source. On Mac and Linux, it would look like this. Either one will work.
And how do I install CompuCell from Conda?
That one, and I'll put the command in the chat. So it's as always with Conda, I recommend creating a new environment. There's the command in the chat. So we have our CompuCell3D Conda channel. That's where we host the actual packages for Twedit, Player, and the computational core, as well as some extensions. And then we use Conda Forge for our dependencies. So that command on Mac, Linux, or Windows, you can use that in preferably a new environment with Python 3.7, but you can also do it in an existing environment. That command you should be able to copy and paste into a terminal. So anyway, yeah, good question. So if you, again, the root directory of the installation as your current directory, you should be able to do something like this, and that will activate the miniconda 3 environment. And then from there, you're good to go. 3. Import CC3D. Just like that. All right, so if it's not clear, no worries. I'm gonna share these slides, and a lot of why I've drawn this up is so you can pretty much just use this as notes, until it sort of becomes routine. So once you've done that, and you can actually successfully execute something like import CC3D, from there you're off to the races. And you can work with CompuCell interactively in a Python terminal, probably more for our applications that we might be interested in. This would be more like being able to execute a Python script really without the help of Player, but instead to be able to call a Python script and have it successfully execute our CompuCell code, but in a more of a general Python context. And what this tends to look like for most applications. Roberto, you got a question?
No, thank nothing. It's noisy here.
Okay, yeah, no worries.
Sorry.
No problem. So the real goal programmatically here is to have a generic Python object that encapsulates a simulation and be able to do interesting and useful things with that object. So the GUI analog here would be loading a simulation in Player and then hitting the start button and starting a simulation and then executing it, watching it do what it does and then stopping it, go make some edits, come back, start, so on and so forth. Have that same sort of functionality, but with a general, like a sort of generic Python object. And that functionality is provided by a class that's in the CompuCell distribution, and you can find it here. So it's in CompuCell setup. It's called CC3D Caller. And what CC3D caller does is essentially the same thing as player. Does all of the initializations, everything that player does when you hit play, all the way to the point of calling your steppable along with the rest of the simulation. And at the bare minimum, this is as simple as just importing this class and then instantiating it while giving the absolute path to the CC3D file of a simulation. So we discussed earlier in our chat about how you can take an existing CompuCell project and just write a Python script around it that uses it. And this is what that looks like. So if you've created your CompuCell simulation, you have a CC3D file and your steppables, maybe some XML. What you're looking at doing here is instantiating a CC3D caller and giving it the absolute path to the CC3D file that was created for you by Twedit. And if you can do that, then the programmatic analog to pressing play in player would be calling its method run. And that's quite literally it. There's plenty more that can be done with this, but as far as taking an existing CompuCell simulation and executing it in Python as a generic Python object and doing whatever your simulation tells CompuCell to do, this is it. Any questions? There's plenty that goes on in the back end to make this happen. There's plenty more functionality that I at least want to sort of pop into your brain so you can maybe get a sense of what all you can do with this. But at the very basic level of what this looks like, this is using CompuCell in a Python, like a generic Python environment. All right, no questions, or put them in the chat. Now this is, I think, one of the most interesting parts, and this hopefully is what can give you maybe some inspiration on how to start really integrating this into potentially, my hope would be into some of your research, which is the information pipeline. Going from this, say, generic Python script that we were just looking at with instantiating our CC3D caller instance and running it. The question for me, at least, that immediately sort of pops into my brain is, well, how do I put information into my simulation? And maybe even more importantly, how do I get information out of my simulation when it's done? If I wanted to, say, do some analysis on simulation data, can I get it here? And then maybe have some more code below it to say, return some information in a function. And so there's a full data pipeline to be able to pass information into a CompuCell simulation, have the CompuCell simulation do stuff, and then send information back. And so I'm going to declare some terminology that's maybe arbitrarily defined, but I find it somewhat helpful to try to distinguish between sort of what we're talking about here during execution. We're going to talk about what I'll refer to as the Python space, which is the area where we do something like instantiating a CC3D caller instance and doing execution. And then the CC3D space, which is what you can think of as where we've been so far in the workshop, all the way up until our conversation right now. So Twedit helps you do stuff inside of the CC3D space. And what we're talking about now is the infrastructure and capabilities associated with doing the CC3D space, but more in conjunction and connection with things that could be going on inside a more general Python space. So you can't, for example, do a loop over cells. We've been doing things like for cell and self.cell list. That is something you would do in the CC3D space. and we want to learn about how we can do stuff in the Python space that may be interconnected with what goes on inside the CC3D space during execution. So all of this is all done in this call. And so we're going to look at how to get some stuff declared here into here, and then send some stuff back right here. All right, so let's look at how to get stuff into a CompuCell simulation. So the CC3D caller instance has a couple of additional keyword arguments that are optional, and the one that's relevant for this conversation is the keyword argument called sim input. And sim input, whatever is passed to it, is essentially forwarded over into the CompuCell, the CC3D space. So when you instantiate a CC3D caller instance, this is a sort of extension of our original example. You'll notice here that there's an additional argument here, sim input equals cell ID. And all I'm looking to do here is just instantiate a CC3D simulation in a Python space and tell the CC3D simulation the ID of a cell that I would like the simulation to get back to me. Just launch the simulation, and whatever ID I choose, that simulation should execute and then give me the cell object back. Whether this will work or not, because of memory issues, is sort of besides the point here. The real point is I'm declaring information in the Python space, having things go on in the CC3D space that correspond to that input, and then return a corresponding value. And in this case, choosing a cell ID. Now, anything can be passed into this sim input argument. In particular, some sort of Python container, typically a dictionary, because it's easiest to sort of coordinate the passing of information to and from these spaces. But whatever gets passed to sim input will show up inside of the CC3D space. There's some current work to make this a little simpler, but for now, as of 4.3.0, and actually I think closer to 4.2, whatever gets passed to sim input is accessible inside of the CC3D space through what's called persistent globals. And you can get persistent globals in the import of your Steppables script with this command here. So it's just an import from CompuCell setup. So from cc3d.compuscell setup, import persistent globals. And just as a sort of a spoiler, persistent globals is the container that holds just about everything going on the Python side of CompuCell. Excuse me. And in this case, whatever is passed to sim input for the CC3D caller constructor gets put on an object for persistent globals called input object. So when cell ID here is passed to sim input, in my CC3D Steppables script, I can say my object equals persistent globals.input object, and they will be the same. And not even just the same by value, they are the same by memory. So it is quite literally migrated over for you into the CC3D space. And so in this example here, if all of my simulation is supposed to do is just get the requested ID of a cell from the Python space, retrieve that cell and send it back. If that's all my simulation is supposed to do, well, this is the step for retrieving the actual input specification from the Python space. And as such, I've named the variables accordingly. So cell ID passed to sim input, cell ID being retrieved during the final call of the CompuCell simulation. And again, that's retrieved from the attribute input object on persistent globals. And then in this case, my simulation goes ahead and does the corresponding internal simulation instruction, which is to fetch the cell by ID. The Steppables have this method defined on its interface, self.fetch cell ID, and passing the requested ID, and there's the cell that's been requested from the Python space. Is that clear?
Why are you doing this in the finish function?
Yeah,
Method.
good question. So the Steppable has you know, a runtime interface. We've mostly this week worked in the start and step methods. But two methods that oftentimes get neglected are called the finish and on stop methods. And I'll put it in the chat just so it's clear. On stop. Finish is called right before the basically the termination of a simulation. And by termination, I mean in a memory sense that you know, you specify a requested number of Monte Carlo steps to have executed in the simulation, and CompuCell will execute all of them unless you interrupt it somehow. And should the CompuCell simulation reach the final step that you requested, you're given a chance to do something like wrap-up work. And whatever wrap-up work you want to do before everything is deleted in memory, that's all prescribed in the finish method. So this is executed after the last step in simulation, but before things start getting torn down, essentially. Now, of course, I could do this in the start method. I could do it every step in the step method at, you know, the expense of additional computational cost. Here I'm just doing it in the finish method. And then the next step then at the very end is to somehow send it back. Is that clear, Pedro?
Yeah, so I could, for example, return the volume of that cell.
That's right. Yep, it's location, the average location of you know, cells by type, velocity, you know, total concentration of a particular field, just about anything.
Yes, this is very powerful. You could do some data processing in finish function and return everything done.
That's right. And in fact, I have a couple of examples prepared to share sort of to that end, showing how to do that. We will not be coding these sorts of things up right now because this can get very intensive very quickly, which tends to amount to getting derailed very quickly. So instead, I wanted to sort of highlight, you know, what can be done and look at it from a conceptual standpoint, and then provide you with resources for where to start on, you know, if anything, hitting me up via email to figure out how to use it in your particular applications. Okay, so that's one half of the information pipeline, getting information into a CompuCell simulation from the Python space. And so obviously then maybe the next question is how to get information back. And maybe you could have guessed it, there's another attribute defined on persistent globals to be able to send something back to the Python space. And in fact, there is. So this same persistent globals that we imported to be able to get the input from the Python space, that persistent globals also has an attribute called return object. And whatever return object is set to is made available on return from the CC3D caller method run. I'll say that again. Whatever return object on persistent globals is set to, in this case, the cell that was fetched, whatever return object gets set to is returned back into the Python space by the CC3D caller method run. Run executes the simulation. When it's completed, it will return an object. It's just a dictionary with a little bit of information in it. The most critical piece of information in that dictionary is whatever you set return object to inside the CC3D space. And so I've got my cell. Choose an ID in the Python space, pass that ID into a simulation, have the simulation get the cell based on whatever was specified, and send it back.
So if I want to return more than one object, I should return them in a list or dictionary, something like that.
Yep. Most often, I think in every application I've either built myself or contributed to or even seen, a dictionary is used to pass information in with some predefined keys and corresponding values. And then another dictionary gets passed back, also with predefined keys and corresponding values. It's essentially like a something like an information pipeline that has something like slots. But yeah, whatever you want. Their memory rules apply, obviously, and part of why I've included this particular example is because it is actually possible to crash an executable with this, depending on how the cell is handled in memory. These workflows tend to be without issue whatsoever when using plain data, passing floats and strings and just a lot of basic data types in and out. No expected problems whatsoever. When it can get dicey and potentially problematic is when you start sending information back into the Python space that CC3D plans on deleting. For example, if you were to try to send, you can access the simulation object on persistent globals, and should you send it back, CompuCell is going to delete it, in which case you're going to get a crash. So, normal memory rules apply here. So when I say sky's the limit, maybe that's a bit of overspeaking, but certainly establishing some very complicated and intensive data pipelines readily available. All right, so this says exercise because it's written like something that you can do as like homework or as just like a sort of practice for kind of like walking through how to do something like this. I've included the link here, and for your reference, so this is included in the CompuCell installations in the demos folder. It's also available online along with the rest of the CompuCell code base on GitHub. So there's the link to this example. But this is a sort of classic use case in a very, very simple problem, which is to calibrate the chemotaxis plugin for single cell migration. So I wrote this in a way that I would write it for an actual integrated application. So this is a far cry from where we've been this week on what looks like sort of a typical CompuCell simulation. This is an executable Python script that you can pull from the installation, run in your activated Conda environment, and this will execute a simulation of single cell migration subject to chemotaxis, and will determine the chemotaxis parameter necessary to produce a predefined velocity, and all using the SciPy optimization module. This I've shared with the hope of demonstrating a sort of simplest sort of use case for an integrated application. For those of you who have worked with SciPy, maybe you spotted this already, that there's this is essentially taking CompuCell and putting it into a black box sort of function that SciPy would understand to do optimization. So you can run that. If you follow the steps to activate the CC3D environment, you can download that script and the corresponding simulation that accompanies it, and that should run out of the box. So try that out whenever is convenient for you. I've got just a couple of I don't know, stimulating questions to maybe get you thinking about how all of this is set up and what it looks like. But I don't want to dive into the details on that at the moment. We can certainly talk about that, and I'd welcome all of you to email me about this, or even hit me up in the chat during some of the other lectures about this. But there's potentially a lot to these sorts of applications where they can be quite simple. And so instead, I want to focus on the concepts and the capabilities, and we can connect as necessary. So I will say I purged the notes instead of including them, but I will say, and Lorenzo's reminded me in private chat, that it is possible to do some of these things with older versions of CompuCell. I just don't recommend it. There's a lot of environment setup that used to be involved in making CompuCell run, and we've eliminated a lot of that in the past couple of releases. And so, yeah, Pedro, CompuCell currently only supports Python 3.7. Yeah, it's currently on our to-dos to support through Python 3.9, if not all the way up to 3.10. So if you're trying anything besides a Python 3.7 Conda environment, it will not work. So yeah, it's possible to do these things with some extra work involved with older versions of CompuCell. If you really want to go that route, you can look at some of the execution scripts in the older distributions of CompuCell. You can sort of deduce the sort of work that used to be required. Now CompuCell does all that setup all on its own. And again, that's per version 4.3 or later. Okay, see some quick questions here. Recording, yeah, so we kind of had to pivot a little bit over some Zoom technicalities. So I'm currently recording this locally on the fly. Thanks again for the reminder. And I'm going to work out with Hayden and James about how to make this available to everyone. So yes, we are recording. Oh, and Lorenzo asks, what's new or what's easier? So yeah, so with 4.3 and 4.3.1, one of the newest parts about being able to set all of this up is the automation of the environment setup. So of all of the work that used to be done, you used to have to do things like set Python path, make the binary location available through environment variables. All of that's done automatically now. So CompuCell now does a lot of introspection that's set up during the build to be able to figure out where all of its installed components are, on the pretense that it's going to happen inside of a Conda environment. And that's it. No other input information required to make something like this work. Just activating the environment that CC3D is installed into, going into Python and typing import CC3D. Literally no other setup required. So this takes the setup that used to require generating at least one additional setup script and having to kind of jump through hoops a little bit, resolves all the way down to going from no CompuCell to CompuCell in Python in exactly 3 lines of commands. Install the environment, or install CompuCell into the environment, activate the environment, and you're ready. Very cool. Excellent question, Lorenzo. If we can get to it, I'm going to show off some other stuff that we're working on for future releases, but we'll see how far we can get. You'll have the slides either way, so you can read about it if we don't get there in time. Okay, so to sort of put this into perspective a little bit, you know, James had talked earlier about some work that we'd done, you know, in viral infection. I mean, this is how, say, I got to meet Lorenzo, for example. You know, we do a lot of investigation of parameters concerning model sensitivity or sensitivity to stochasticity. You know, again, these are stochastic models. The POTS algorithm is intrinsically stochastic, and whether or not a particular model is sensitive to its stochastic dynamics is almost always a question of interest, let alone actually investigating the sensitivity of the model to particular mechanisms. And when a simulation is expensive, like say the calcium signaling or the calcium wave simulation that James showed earlier today, you know, it took a couple of minutes of waiting just to see one wave propagate. And you know, if you are, say, interested in what the sensitivity of, say, the rate of propagation of those waves, what the sensitivity of that propagation rate is to, say, the parameter VPLC. He talked about the critical control parameter for the production of PLC. If you were interested in the sensitivity of like those emergent waves, say you wanted to do something like a parameter sweep, if you really want to have to wait 5 minutes in player to let one simulation execute, but you want to, say, do 50 instances to test for stochasticity and, say, maybe test 50 parameters. It's a lot of simulations to just sit and watch player execute. The capability that you have with the CC3D Python API sort of automates all of that, essentially, because you now know, you know, at least conceptually, and in the notes for reference, you know how to now set up a CC3D caller instance, having a generic object that can take your information and execute a simulation and give information back. That can be used in Python loops, conditionals, even in multiprocessing. It all works. And so setting up these sweeps then becomes a matter of just doing things like for loops. And in this case, so this is for the sort of viral infection framework that we worked on in the early days of the pandemic. You know, we were interested in some specific therapeutics, in particular antivirals, and the timing of the administering of antivirals after the onset of actual infection. There's a lot to investigate with this model. Even doing a parameter sweep like this, you're sitting and manually accomplishing this in player would take weeks of absolute boredom. Multiple instances of different timings of when this therapy is administered. That's what you see here in the dashed line. Varying potency of the drug that's being administered. These simulations took 15 minutes. We did 10 different trials of each of these sets of parameters. Watching a simulation run one after another in serial is about 160 hours of simulation time. Whereas putting this together in a Python script using the Python API, I dumped this on one of IU's supercomputers, and this was done before dinner. So 8 hours of simulation to do what would have been 160 plus hours of babysitting player as it executed one simulation after another. And this is sort of the, you know, the entry point of developing these sorts of workflows, because quite literally setting up something like this is really only a couple more lines of code from the code that we were just looking at. If I jump back to our example here, with just passing in a cell ID, getting the cell ID and passing it back, if I had, say, a list of parameter values that I wanted to execute, nothing stops me from doing this in a loop over all of the values in a list, getting information back from my simulation. I mean, not much more work to go from this highly oversimplified example to something that got published and was really interesting. So there's a lot of capability with just this very basic functionality of having these generic simulation containers. Any questions? Oh, sorry, Nasheen, I missed one of your questions. You're gonna do the same tonight, and am I using Anaconda? I use Miniconda, which is just a much smaller version of the full Anaconda installation, and either will work. Depending on your platform or your operating system. Actually, no, just either will work. It's really as simple as that. And if you run into any trouble, either send me an email or try. Their documentation for supporting Anaconda is also great. So yeah, you should be able to get through it, no trouble. All right, and this I think maybe, well, my hope is that this can take us, a bit beyond where we've been so far this week. In that, we've really been working in the paradigm of that we have this sort of sandbox that CompuCell creates for us in our Steppable, or you can have multiple Steppables, that do all sorts of interesting things inside the simulation. What I really want to do is to broaden your perspective on what else can actually be done with a CompuCell simulation. Because if you have this ability to develop a simulation and then say provide something like a container for that simulation that can be executed and it can handle inputs and make decisions internally based on that, and then pass information back, you then have the ability to develop highly specialized simulations for integrated applications. This essentially provides a way to develop something like integrated software that can be deployed in these advanced numerical and computational pipelines. A Steppable, which very often is really just treated as a means for executing a simulation, a Steppable really can provide more capability than just executing your model. A Steppable can also be used to, say, execute instructions to support something like a service. That your simulation, whether it's for your own ends or whether it's for, say, sharing with a scientific community or even just a research group, that your Steppable can do more than just execute your model. It can execute your model according to specific pipelines that your simulation may be useful for supporting. And the sort of classic example that I like to provide for this is actually the viral infection framework that is demonstrated here. So this computational framework for viral infection is actually quite complicated, with a lot of different models involved in it. And each of those models is implemented in a particular Steppable, but each of those Steppables are actually designed so that they can be interchangeably used and also adapted based on what some user outside of our group may be interested in studying. Even to handling things like information about the discretization of a space. So this is an excerpt from the sort of main Python script that we tend to neglect in like classic CompuCell development. Two Python scripts are created, but really only one of them is actually used, and that's the one with the Steppables script. But this is what this main Python script actually looks like for the viral infection framework. And you can see that a lot is actually being done with it besides just giving the Steppable to CompuCell for execution. This is actually taking input about what the spatial and temporal discretization of this simulation is. And that's handling that in such a way that it actually synchronizes with all of the other Steppables that are executed along with the simulation. This is an internal detail for this particular application, but what's important to note here is that your Steppable, just like any other Python class, can be tailored to do whatever you want, along with the capability that it already provides for executing CompuCell models and simulations. The point here that I really want to drive home is that it's very possible, and we found when doing this work for this viral infection framework, that it's not just possible, it's actually quite straightforward to develop community developed models and simulations where groups can co-develop different aspects of the same simulation just by following basic, I'd say like sort of classic programming principles. Encapsulation, your Steppable, well defines a mechanism for encapsulating your model in a way where it can be used with other models simultaneously, whether you develop those other models or you just shared your Steppable with a community who also want to use it. So this is open source, community driven model and simulation development, just waiting to happen. And the viral infection framework shows that it works. And I'm very excited about this, obviously. I'd be happy to talk more with others, about this more, maybe in private, or I can share the source code for this framework as well, because this is publicly available. But I really want to, for those of you who are more programmatically inclined, you've learned how to use a Steppable for modeling and simulation, but I want to bring back to the point that this is still basic Python programming, and these Steppables really can provide a way to do this sort of group or community based simulation development. And this is really what it looked like for the viral infection framework, and this is how we cast it. So we provide a bunch of built-in models for various aspects of viral infection, viral internalization and release and immune response components and all of that, and setting this framework up to function like an additional set of built-in Python modules, just like how you would import random, or you would import math or multiprocessing, all of the modules that come along with every Python version you've ever used, to do the same thing, but with Steppables that define models, whether they were developed by you or they were developed by someone else and shared, or whether they were developed by you, which you developed by working off of something that was developed by someone else. The same basic Python applies. And the Steppable provides a really nice mechanism for being able to take model and simulation specification and combine that with the well-known power of just basic Python. And it really can do things like this. And really not with a lot of, a good bit of thinking, but not a ton of work. I've worked on harder problems than this. And yet this, turned out quite nicely with respect to, what's sort of like standard modeling practice. Anyway, so we do have a couple of extra minutes before we need to head back. So I've got sneak peeks for currently unreleased features that are sort of along the lines of what all of this that we've looked at so far was really for. But I first want to pause and ask, are there any questions about what we've talked about so far? Is anything of interest that anyone would like to discuss more before I go advertising for future CompuCell stuff? All right, if you think of any questions, either put them in the chat or just unmute and interrupt me. Otherwise, I'm going to show you what we've been working on and what CompuCell is going to look like in the future. So the few minutes I have left with you, this effort towards bringing CompuCell to more of general Python applications, what we've looked at so far was really sort of only the start of it. And some current work that we have accomplished and is scheduled for, it's been scheduled for the last 3 releases, but we keep pushing it back for various reasons. CompuCell will, in a very near future release, not rely on the XML. For specifying plugins and diffusion solvers and the core specifications for like the size of your simulation domain. You do this with the CC3D ML currently. So you've got an XML script, a Python Steppable script, and then another Python script, and it brings all together somehow. The goal really is to also be able to do everything, and I mean literally everything, for a CompuCell simulation, all with interactive Python objects. And you already have Steppables that you've been working with. The goal of this project that is done, just not released yet, is everything that you do in the markup language currently, but instead being able to do it in the same way that you develop your Steppables. So I call this core specs, which is a specification for core CompuCell functionality. No better example than the specification for the POTS object, where you specify the dimensionality of your lattice, you specify the neighbor order. It's the very first couple of blocks that show up in your markup language. Instead, having a Python object that you can instantiate and register just like you would with a Steppable. CompuCell is not deprecating CC3D ML. Instead, the interface is expanding to have the option of being able to do the mixed language approach that's typically done currently. Instead, be able to have just one Python script that can register both plugin and Steppable information as well as custom Steppable information, all like this. Question?
So first, this is a huge progress for CompuCell, in my opinion. I'm really impressed by that. And I am wondering if with this type of setup for the simulation, you could, for example, change the dimensions in the middle of the simulation, or loop over different types of plugin, for example.
Yes, excellent question. So one of the reasons that we've actually been pushing back releasing this has been because of the issue of constraining what can be changed during simulation versus what cannot. Because there are things about CompuCell that intrinsically cannot be easily changed, if at all. Adding a field to a diffusion solver mid-simulation is not possible, and I don't know if it ever will be. Whereas like changing the maximum step to simulate is very easy to change. And so really what is possible for changing during simulation versus what is not is actually a lot of what's been so difficult about finishing this interface. Because one of the main features about this is that every core specification, whether it's in the contact plugin, the POTS core, a diffusion solver, anything that's actually registered will be accessible inside the Steppables to be able to change things just as an attribute on the Steppable. I think I may actually, no, I don't have an example here, but oh yeah, right here. So this is just a little excerpt. So if, say, you were to use the contact plugin, as we typically do through this mechanism, having a Python core specification and for the contact plugin, and that gets registered with CompuCell, then once you're actually inside the CompuCell simulation, inside a Steppable, you'll be able to actually get that spec back and change things on it. So changing simulation like plugin and Steppable details during simulation on the fly from inside of a Steppable. So yeah, excellent question. Some things really can't change during a simulation, and other things are readily settable. So yeah, a lot of the work that's really left is you know, really well defining what you're allowed to change versus what you're not. Yeah, it's a good question. Oh, let's see. So yeah, I'm really excited about this. One of the other big things that sort of takes this this capability that we've looked at today to the absolute maximum is what I call CC3D as a service. So we've already talked a little bit about you know, really what it takes to execute a simulation in a general Python environment. This capability here for CC3D as a service takes that to the maximum on the memory side of things to make it possible to execute multiple simulations in the same memory space concurrently and also interactively, which is to say that this capability for CC3D as a service will allow you to launch as many simulations as your hardware can suffer through, have them all loaded, execute them manually, and even be able to share information between them as they execute. The execution of which is totally under your control. So what we looked at today was the CC3D caller capability of being able to execute a simulation by calling its method run. What we're talking about here is instead having a live object that you can call step on, where when you call step, a simulation step is executed, and then it goes back to an idle state, having a live interactive simulation or a set of live interactive simulations that are all totally under your control. That is interactive CC3D as a service. And the best part about that, and I could lecture on it separately, so I'm going to try to not get into the details too much on it, but this includes the capability of being able to particularize the interface of the services that are created, but from within the simulation specification itself. So let me see if I have an example of this. I do. Okay, so this is an example of what this looks like. So say we're in our Python space here. We got to wrap this up here in a minute so we can head back to the main room. Say we're in our Python space, just working with what we would have been doing with a CC3D caller. Instead, we're using a CC3D service. And this also gives us an object that also is a container for a simulation. So there's a simulation inside here. And I'm also calling run on it. But you'll notice that I'm doing more with it in the rest of the code. And that is because run doesn't actually execute the simulation according to the maximum number of steps and all of that. Instead, what it's saying is run the service and then return so I can do stuff with that service, like initialize the steppables inside of it, and then call all of the start methods on all of the steppables, and then step through it as much as I want and get information from it in my Python space as I execute it. And based on some logic that's totally external to CompuCell, either continue executing or finish. And what's even better is that I can add methods to that object that's returned to get specific data immediately from my service, but based on the interface that's defined from inside the steppable itself. If you're at all interested in this capability, they're on the back end side, because this is provided by a separate library that I wrote that is also open source. I'd be happy to share and discuss it with you. But this makes this possible. This is my last slide. This is really what I wanted to share with you today. So we're finishing up the sort of finale of the Python API for CompuCell, which is full support for interactive CompuCell simulations in IPython and Jupyter. And this is what it looks like here to the right. Been working for about a year now with a student, Trinity Chung. She's at Pasadena Community College and starts at UCLA in a couple weeks. She's helped us a lot with developing the control features for doing interactive visualization. But essentially this is Player, but inside a Jupyter notebook. It's Twedit and Player, but all in Jupyter. So when this capability is released, you'll be able to create a CompuCell simulation all inside of a Jupyter notebook, generate fields that are interactive just as they are in Player. This is the same visualization pipeline that's done in Player, but instead now it's occurring in Jupyter. Quite literally everything in Python in a document that you can publish online, you can share with your friends, you know, everything about Twedit and Player, but instead in HTML. So that's all I've got. That's my final teaser for upcoming capability. We got to be back in 2 minutes. So let me ask last second, any last minute questions that I can answer, or any comments, really anything. Let me open the floor up to everyone before we head back.
If nobody has any questions, I have one.
Yeah, go for it, Pedro.
So it's a very silly question. One of my students asked me, and I didn't know how to answer. And probably you were the right guy. Basically, he asked me if it would be possible to, for example, simulate a tumor, simulate a cell, something live in a game, for example, Minecraft. How feasible would it be?
I mean, concerning the visualization, or being able to?
Yes, just simulating CompuCell, and you can visualize inside the game and jump over it, etc.
Oh, I mean, concerning the interactivity, you know, of being able to manually manipulate simulation data based on something like mouse and keyboard events. You know, those are things that can be implemented, though CompuCell doesn't, you know, really natively support. The visualization, you know, is already there. You know, can generate a three-dimensional simulation, you can visualize it in 3D, and you can navigate around it. So concerning the actual visualization, that's there and made available. You know, the interactivity to that extent is not something that CompuCell, I mean, that's certainly something that, you know, some of our other projects lean into a lot. But CompuCell, not so much. It could be done, but it's not really been as much of a focus. But if you are interested in interactive simulation to that degree, I'm always happy to talk about my other main simulation package that I've refrained from spending our time on today. But it can be done. Simulations can be interacted with in real time during execution. And I know it because I do it. And I'm
Nice. So you could, for example, make a tumor and make a cut through it, like for example with your mouse, cut and see what happens, for example.
That's right.
This is very cool.
I agree. All right, excellent question. Thank you, Pedro. All right, so I believe that we're out of time. So let me make sure real quick that everyone has the link ready to be able to get back. I believe we are all due back in the main room, have already been brought back to the main room. No, I'm still in my room. Okay, so thank you all again. Let's all head back to the main room and I'll see you all there. Thank you so much.
Thank you.